In this video, we're going to look at the comparison tests. In this first example, I have the series from 0 to infinity of 1 over 3 raised to the n plus 1. So I'm going to use the comparison test here. And remember, the basics of the comparison test is if b sub n, which will be the series we're going to compare our original series to, is greater than a sub n, then we can only prove convergence. And if b sub n is less than a sub n, then we can only prove divergence. So if we create a b sub n and it's greater than a sub n and b sub n diverges, then we cannot use that conclusion and we'd have to use a different test. So in the problem we have here, we're going to use b sub n as 1 over 3 raised to the n. So now we're going to look at the series 1 over 3 raised to the n. And if we rewrite this, we could say that this is the same as 1 over 3 all raised to the n. So now if we go back and we look at b sub n, we have 1 over 3 raised to the n. And so in order to get this b sub n, we took the 1 away, so we made the denominator smaller. And because the denominator is smaller, the overall number is bigger. So we made this greater than a sub n. So now when we look at the series that we created, we know that 1 over 3 all raised to the n is a geoseries. And because r, the absolute value of r, is less than 1, we know it's convergent. So we can say that the series from 0 to infinity of 1/3 raised to the n is convergent by geometric series or geoseries. And because it was convergent, we're going to say that a sub n is convergent. So therefore, our original series is convergent by comparison. In the next example, I have the series from n is equal to 2 to infinity of 1 divided by the square root of n minus 1. And again, we're going to use the comparison test. And I'm going to say that my b sub n is equal to 1 over the square root of n. And so I added 1 to the denominator, so it made the denominator bigger. So our overall number is smaller, so b sub n is less than a sub n. And now we're going to look at the series of 1 over the square root of n. And 1 over the square root of n is our p series. And we could say that the square root of n is also n to the 1/2, so p is less than or equal to 1. So this series is divergent by p series. And because b sub n is less than a sub n and b sub n was divergent, we can also say that our original series is divergent. And it's divergent by comparison. In this last example I have the series from n is equal to 1 to infinity of 2n squared minus 1 all divided by 3n to the 5th plus 2n plus 1. And in this example, we're going to use the limit comparison test. And the limit comparison is going to be a little bit easier to use because we're going to make changes to the numerator and the denominator, and it would be harder to tell if you're making b sub n greater or less than a sub n. So the limit comparison test says if we take the limit as n goes to infinity of a sub n divided by b sub n, and it's going to be equal to c. If c is greater than 0, then both series converge. So we're going to say that in this problem, b sub n is equal to n squared over n to the fifth. So I took the n with the largest exponent out of the numerator and the denominator, and I made it my b sub n. And we can simplify this to 1 over n cubed. And now we have the limit as n goes to infinity of a sub n, which is 2n squared minus 1, divided by 3n to the fifth plus 2n plus 1, divided by 1 over n cubed. And remember, when you divide a fraction over a fraction, you can multiply by the reciprocal. So I'm going to write it as n cubed over 1. And now, if we were to multiply these two together, we have the limit as n goes to infinity of 2n to the fifth minus n cubed divided by 3n to the fifth plus 2n plus 1. So our limit here is equal to 2/3. And since 2/3 is greater than 0, we know that this is convergent. So we can say that the series from n is equal to 1 to infinity, 2n squared minus 1 over 3n to the fifth plus 2n plus 1 is convergent by the limit comparison test. And that's all for our video on comparison tests.